Okay, so how you guys doing? Lisa, how you doing?
Tired.
You tired? It's only week 3.
I work open and close all weekend.
Oh, where do you work?
I have pharmacy in Lansing.
Ah, okay. Alexis, how you doing?
Hey, it was Alyssa.
How you doing?
Tired.
How you doing? It's tired too?
Yeah.
Okay. I'll try to be a little bit more entertaining. I don't promise anything.
If I fall asleep, it's not on you, and you can call me out. That's fine. I'll respect that today.
That's fine. Paige, how you doing?
Oh, just dandy.
Just dandy?
Yeah, absolutely.
Good. Was a good weekend?
It was a good weekend, yeah.
Cool. Valerie, how's it going?
Good.
So, is there anything like how's it been with the online lessons? Yeah, things make sense.
Yeah.
Is there anything you want me to go over? Do you want me to review anything? Everything perfect? Wow, I'm an awesome teacher. Okay, so the last thing that we talked about on Friday was uh, about friction, and we talk about different kind of frictions, and we basically talk about having like uh, two stages of friction. So we have static friction when an object doesn't move, and then we have kinetic friction when an object's kind of moving. And the main difference is that when you have a static friction, uh, as you push harder, the static friction is gonna match your strength and is gonna keep the object in equilibrium. So if the object is not moving, because that's the condition that we have, and you push with 10 newtons, then the friction is going to be 10 newtons. And if you push with 50 newtons, the friction is going to be 50 newtons. And it's going to keep increasing until you reach a threshold. And once you reach the threshold, the object is going to start moving. And when the object moves, the friction kind of falls down really, really fast and then remains constant. And once it starts moving, this friction is going to be constant regardless of how much force you apply or regardless how fast the object is moving. So it's always going to be the same. Okay. Then we talk about the static friction because of this ramp. Well, it's going to have a value from 0 to a maximum value. And that maximum value is calculated by this coefficient mu s and the normal force. And again, this is the maximum value. And the static friction is a constant. And the way we calculate it is mu k, which is another coefficient, times the normal force. Okay, so you can see how the normal force affects the friction force. And remember that the normal force is also going to depend on the mass of the object. So the more mass you have, the more mass you have, the higher the normal force is going to be affected by the tilted angle and what surface you have. But in general, you can make the assumption that given a surface, if you have two masses on that surface and one has a higher mass than the other, then the one with higher mass is also going to have a higher normal force. And because of that, then you can imagine, okay, heavier objects are more difficult to move because they have a higher friction. Okay? So that's more or less what we talked on Friday. Is there any questions about this? Nope. Okay. So what I want to do to
Question about I'm looking at my notes compared to those, and I don't know if I just wrote it wrong, but the steel, I have them like, I have 0.1 and then 0.05.
Oh, let me double check. There's a table on your book, and we'll use the values on your book. And if I'm talking about different kind of materials, I will give you the coefficient. So there's really not a way to calculate. There's not a question to give you the value of mu s or mu k. You need to calculate. You need to do an experiment to calculate them, or or they have to be data on the program.
I just didn't know if that was something we needed to memorize.
No, no, no. No, I don't. That's what I always get them wrong. For steel and steel, it's 0.1 and 0.5. So yeah. So I gave the other class the wrong numbers. You see? I like you guys. Yeah. Okay. So what I want to do today, instead of keep moving on different topic, I want to do a couple of problems involving friction. And hopefully it will make a little more sense, and also will help you practice problem solving. Okay, make sense? Okay. So imagine that you are trying to move, you're helping a friend that you are trying to move a sofa and the mass of this sofa is 50 kilograms. Okay, you have, you're moving the sofa on a carpet, so on the sofa you put one of those little discs that helps you to move things. And those discs, you know that the kinetic coefficient, the kinetic friction coefficient is going to be 0.8. Okay. Now you're going to start pushing, and you push, and when this sofa starts moving, it's going to move at a constant velocity of 0.4 meters per second. Okay. What I want to find out is what is the force. So I'm going to be pushing here. So what I want to find out is what is the force. Okay. Make sense? You want to try on your own? Okay.
I mean, we can give it a go, but
Okay.
I am.
Let's start with the free body diagram. Let's start with trying to figure out what are the equations that you need to solve. So what kind of conditions do we have? Do we have a dynamic problem? Do we have a static equilibrium? We have a dynamic equilibrium. And then try to write down the equations that you need to solve. And if you get stuck there, then we'll do it together. So now just you have studied and you have a macro, for example, you have and what are the equations that will help you to solve that condition. Okay. So I think almost everybody got the right Kuboid diagram. So remember the normal force always have to be perpendicular to the surface. So this is the force as a push. So you still yeah, so this is the force that you are pushing, you have the friction force. Can you make drawings of that?
I tried, I could, at least not here, I went on Google, didn't see there and told me that, just using WordPad.
So you need paper or?
I'll be fine, I can visualize it.
Okay. No. Keep going till you get stuck. So the first thing you need to find out is what kind of system do you have? So do you have a static equilibrium or dynamic? So you need to find that. And then based on that, you can see what equations you need. Okay, so start there, and if you get stuck again, so if I solve the problem on the blackboard or in the piece of paper, everybody's like, oh, that's easy, I know how to do that. But it's when you try to do it on your own, it's like, oh crap, I don't know how to go from point A to point B. So try to find out what kind of problem do you have with dynamic equilibrium, static equilibrium. Yes, I think pretty much everybody got I think pretty much everybody got the right free body diagram. So your free body diagram should look something like this. So you have the force that you're using to push, you have the weight, you have friction, you have normal force. this is a pretty straightforward free body diagram. So once you have this, what you need to find out is, okay, what kind of problem do we have? Do we have a static equilibrium? Do we have a dynamic equilibrium? Do we have a dynamic problem? So Jacob, what kind of problems do we have? So we have a dynamic equilibrium. Because we have a constant speed. Okay. So what are the equations? So if we have a constant speed, the sum of forces in x has to be equal to what? Alexis.
Yeah.
So if we have a dynamic equilibrium, then the forces in x has to be equal to what? Oh, the forces in x.
Oh, it's gonna be the friction force plus the force applying.
Mm-hmm. Equals to
0.
y.
I don't know.
Alisa? Because dynamic equilibrium, because there's no acceleration. Okay? You got it. It's okay. Don't get nervous. So this is the equation that we need to solve. We have another similar equation in the y direction, Aubrey.
Normal force minus the force of the weight equals 0.
Yeah. Again, this is 0 because there's no displacement in the y direction. Yes.
Why is that one minus?
This,
The force?
yeah. So the weight is pulling down in the y direction. So that's what we have it in the different.
So you choose your free body diagram and decide. Okay, thank
Yep.
you.
So I'm gonna call this equation 1. I'm gonna call this equation 2. And now from equation 1, I need to solve for the friction. I mean, I need to solve for this force, right? So I'm gonna have friction plus this force is gonna be equal to 0. I know that friction is gonna be negative, and this friction is a kinetic friction. So this is gonna be negative mu k times the normal force plus the applied force is going to be equal to 0. So the applied force will be mu k times the normal force. Pretty much. That's it. Now, I know the value of mu k. Mu k is going to be 0.8, but I don't know the normal force. So I need to find that normal force. So for that one, I'm going to use equation 2. And equation 2, normal force minus the weight is equal to 0. So the normal force is going to be the weight, and that's it. So I can substitute this here, and I'm going to say, okay, the applied force is going to be mu k times the normal force. And once I have it like that, I can substitute values and say, okay, this is going to be 0.8. The mass is 50 kilograms. And gravity is 9.8. And from there, I can find the force. Aubrey, did you get a value?
490.
490? Okay, but
Wait, for the
applied
applied
force.
force, 392.
Yeah, I like to say, it looks small.
She said that was the applied force.
Yeah, that will be the amount that you need to push for that couch to move at a constant velocity. It really doesn't matter if you're pushing at 0.4 or at 10 meters per second, you just need this force for that object to move at that constant velocity. Okay, make sense? Yeah. Okay, so do the same problem. Do the same problem, but now the couch is going to be moving from 0 meters per second to 2 meters per second in 3 seconds. So what I want you to start pushing, and as you push, the couch is going to be moving faster, faster, faster. So what will be that force that you need in order to have this change in velocity in this time? So you're going from 0 meters per second, so from static position to 2 meters per second, and you do that change in 3 seconds. So what will need the force that you need to apply? So again, start with the free-body diagram. Look what time conditions you satisfy, and then look at that and pick the right force.
So this is the mass,
Yeah,
the weight,
the mass,
the mass 50,
yeah,
and
times acceleration.
Okay, mass acceleration.
Yeah.
Yeah, this has to be newtons,
Oh, and newtons.
and the acceleration is okay. So, so these are the forces that you have in x, and this are equals to n ax. So this what forces you have in x? So those two forces have to be equal to n.
Okay, so the free body diagram for this problem looks exactly the same as the one that we just did. So we're gonna have, we have the weight, we have the normal force, we have the applied force, and then we have friction. Okay, that's our free body diagram. I think, Paige, you have attention over there.
Oh, yeah.
Now, in this case, also, what kind of problem do we have? Do we have a dynamic equilibrium, static equilibrium, dynamic? Why? Because it's changing velocity. Yeah. So we have a dynamic problem. Okay. So, Noah, what kind of equation do I need for a dynamic problem to describe a dynamic problem?
Well, you need to figure out how much force you need to apply on the object to make it go faster than a equilibrium speed.
So,
Force equals mass times acceleration.
so the big change is that now the forces in x are going to be equals to, instead of being equals to 0, now it's going to be equals to mass times acceleration. We're going to look specifically at the acceleration in x. In the y direction, the couch is not moving, it's not being displaced in y. So we're going to have that all the forces in y has to be equals to 0. Okay? So we need to find this acceleration in order to solve this problem. Yes. Oh. So in the y direction, the object is not being displaced. It's not being translated in the y direction. It's only moving in the x direction. So what I need to do now is to find this acceleration in x. So I know that in x, the definition of acceleration is change in velocity respect of time. So it means that goes from 0 to 2 meters per second. That's a change in velocity. And I do this in 3 seconds. So my acceleration is going to be 0.67 meters per second square. Yeah? Make sense? Okay. So I'm going to start with my equations in the x direction. And I'm going to have, in the x direction, I have friction plus the applied force equals mass times acceleration. Friction is going to be minus mu k times the normal force, negative because it's pointing in the opposite direction of the motion. The applied force is what I want to find out, and the max is what I just calculated. The mass is going to be 50, and the acceleration is the one I just calculated. So from here, I can solve for the applied force. And again, this is the equation that I need, but I need to find the normal force. So to find the normal force, I need to work in the y direction. And in the y direction, I'm going to have two forces. I'm going to have the normal force, and I have the weight. And they have to be in balance. They have to be in static equilibrium. There's no motion or displacement in the y direction. So the normal force is what I want to find out. The weight is going to be negative, so that's going to be minus the mass times gravity. So the same as last time, the normal force is going to be mass times gravity. And again, when you have a flat surface and you don't have any forces in the y direction, there's no ropes pulling up or someone pushing down or whatever, this is going to be almost always the case. The normal force is going to be equal to mass times gravity. So now that I have this, I can substitute back. So this is 3 and this is 4. Then I can substitute 4 into 3. And then I'm going to have plus mu k mg. Okay. And from there, I can just substitute values. You can factor out some things here and there, but it's not necessary. So you have 50 times 0.67 plus 0.8 times 50 times 9.8. And I got 425 newtons. Yeah. H makes sense?
Yeah.
Yeah. Alexis? Trinity? Jacob? Alex? Okay. So now we have a ramp, and we have a ramp, and let's say this ramp has an angle of 20 degrees. Okay. On this ramp, you have a wooden box. And this wooden box has a mass of 30 kilograms. Okay. The friction coefficient, the static friction coefficient between the floor and the wood and the crate is going to be 0.8. And I'm going to assume that the box is not moving. And I want to find out what is the value of the static friction. Now, in this problem, try to change your frame of reference. Now, the x-axis is parallel to the ground. That will help you simplify a little bit of the math. Dylan, what can you not say?
I was trying to see the letter after that.
After
What is
that's S. But the normal force is not going to be mg because now it's still.
Oh, wait, no, wait.
Now the free body diagram is going to look a little bit different because now you're around. Yeah, so what I do is usually I just, when you're doing right now, you just do the axis to the drawing. And then you just look at the forces. So which way is going to be driving?
But I feel like that one.
Just drag into your terrain. But just plug out. Gravity. Gravity always goes down, just straight down. It doesn't follow and just goes
So it
just
doesn't
go down. It doesn't go with the axis.
So now,
So now gravity always goes down.
oh, so that's why it is.
Yeah. There are no forces that go like these. That's the calculation.
So it's the way it goes.
Yeah.
It should be 20 degrees that way.
And we don't have enough pliers.
Okay.
So if you do it like that, you're gonna have to solve the equations in x and y direction. Because now, yes, but there's the normal force. You define the normal force to find the friction. And now we know, of course, that components x and y, so it's gonna be a little more complicated. So it's better if you tell the frame of reference at find the friction. And now that you learn the frame of reference here. And then you know that friction is number like this, and then you simplify it from a little. Gravity is going to be implied for weight. So yes. Okay. You have the friction, you have the normal force. And then you need to look at what are the possibilities we have in the x direction. So this is the maximum value that the static friction force can have. Doesn't necessarily mean that under these conditions you're going to have this value.
Okay.
Remember that the static friction can go between 0 and this. So I want to know where in that range is it right now.
Okay.
Yeah?
Good. That's-
Okay, so this is good. So from here you can take what is the normal force.
Right.
And then the friction. Now this is just a coefficient. So we'll solve. Okay.
Okay, got it. So I'm gonna do I'm gonna draw my forces here. So I'm gonna have the weight. I have the normal force, and I'm gonna have friction, and this direction. And drawing my axis here. This is my x-axis, and this is my y-axis. I can see that the friction is along the x-axis, the negative x-axis, normal force is along the y-axis, and the weight is somewhere on the fourth quadrant. So I can redraw my free body diagram, and now it's gonna look like this. So this is gonna be weight, this is gonna be 20 degrees, same angle as the ramp, normal force, and this is going to be friction. Now, this friction that I have here, I don't know if that friction is going to be the maximum friction or not. So I'm going to say, well, that value of Fs is going to be between 0 and the maximum value. This maximum value, that's going to be 1/8 times the normal force. I don't know what is that, but I hope that my friction is going to be somewhere between 0 and 0.8 times the normal force. Okay. Second, the box is not moving. So this is a static problem, static equilibrium. So that basically means that all the forces in X has to be equal to 0, and all the forces in Y has to be equal to 0. Those are going to be the two conditions that I need. I'm going to start with the Y direction this time. So in the Y direction, I'm going to have two forces. I'm going to have the normal force, and I'm going to have the Y component of the weight. And that's going to be equal to 0. The normal force is what I want to find out. The weight is going to be mass times gravity cosine of 20. That's going to be equal to 0, negative because it's pulling down. So the normal force is going to be mg cosine of 20. Oops. Actually, I don't think you need the normal force. Okay, in the Y direction, in the X direction, yeah, you don't need the normal force. In the X direction, we have two forces again. We have the X component of the weight, and we have the friction force. So I'm going to have the friction plus the X component of the weight is going to be equal to 0. Okay, friction is going to go in the negative direction. And the X component of the weight is going to be positive. So that's going to be mg sine of 20. And that's going to be equal to 0. So the force of friction that I have is going to be mg sine of 20. Oops. And that's going to be 100.5 newtons. So if you calculate the maximum static friction, so if you calculate this maximum value, and we know the normal force, and we know the normal force from this equation over here, you're going to end up with a value of 221 newtons. So you will need to push with this force a little bit bigger than this force for the box to start moving. Anything below this, the box is static. So that's what we have in this case. Okay? Makes sense? Alice, is it making sense now?
The problem is itself makes sense, but I'm still really struggling with figuring out which trig function to use to get what you need. Like, I don't know when to use sine and cosine.
So the best way, or the one way that I found, I don't know if anyone else has a different technique. So in this particular example, What I don't want you to do is to think that every time you're working with X component, it's always going to be cosine, and every time you are working with Y component, it's going to be sine, because that's not the truth. It depends on the angle that you have. So in this case, the one that we're just working around, I can give you this angle, the 20-degree angle, and you can draw a triangle rectangle. Like that. So under this triangle, this will be the opposite, and this will be the adjacent side, right? So the adjacent in this case is going to be the Y component, and the opposite is going to be the X component. So if I want to calculate the adjacent side, well, the trigonometric function that has that is cosine of theta is adjacent, thank you, over hypotenuse. And if I want, so this will be for the Y component, and I will use sine of theta for the X component. But I can give you the same body diagram. But instead of giving you this 70-degree angle, I give you this. Instead of giving you a 20-degree angle, so I give you the 70-degree angle. So in this case, I can still do a triangle rectangle, but now it's going to look like this. So in this case, the opposite side will be my Y component, and my adjacent side will be X. So it's kind of flipped, but because you are using complement angles, you get the same numbers. So my suggestion is always, if you have trouble trying to figure out what angle to use or what trigonometric function, just write them down like this. This is opposite of adjacent. Do your triangle, identify your triangle rectangle, and then look which one is your opposite, which one is going to be your adjacent, and then try to figure out what is the right one. That's the easiest way. It may not be the fastest way, but it can help you visualize a little bit more. I think when people have a little more experience and they're more comfortable with trigonometric functions, they can identify it right away. I still need to do the triangle because I'm more visual. So
I'm confused though, like, so you don't know your hypotenuse, so how can you solve cosine?
you do know your hypotenuse because in this case, this is your weight.
Okay.
That is your weight, the vector that you calculate. So,
Okay.
yep. Any other question? No? Is it making sense or not so much? Okay, we'll do a couple more problems on friction next class, and then we'll move to the next chapter. Okay? If you have no questions, then I'll see you guys on Wednesday.